Can you use the integral test to determine the convergence of this series? Well, you can try. We can try. Let's take a look at this. What does the integral test tell us? The integral test theorem tells us. So it tells us that if you have a function that is defined on some interval from some starting point to until infinity, and it maps into the positive integers, this is very important. And the third thing is that you can describe this, I want to say this word, discretization. Discretization is when you take something that's continuous and you divide it into parts. So here I have the continuous integral or the continuous function, and I'm only considering bits of it or integer n. So for example, I have f of x is equal to x. This is a continuous function that looks like this. But if I want to discretize this, it's a difficult word. If I want to do this thing, discretization, I only look at the values of the function at integer numbers. So, you know, I think you know how to count. This is 1, 2, 3, minus 1, minus 2, minus 3. And this is a simple function. I mean, it's just f of x is equal to x. So instead of considering the whole function, we can write a sequence of integers, which gives us the output when we input this n. So what happens then? So you take the integral. If the integral converges, then the series converges. If the integral diverges, then the series also diverges. Luckily, this is a theorem, so somebody has already written down the proof, and we don't need to supply the proof. I will keep this for a moment. If we would like to combine this piece of information with data we have from here, you clearly see this is a sum and that is a sum. We want to be able to say something about the integral. So this is the discretization of what function is my question. First off, does it map into positive reals? The answer is yes, because every single element in here is going to be positive. What function, so it's a reverse question, what function, when we put n, we get the sequence of an, which is n e to the minus n. Well, this is very simple, right? I mean, all right, just replace the n with x and make x be any real number. Well, not any real number in this interval. And then you're done. Actually, in this case, k is equal to, do you know what k is equal to in this case? In our case? It's equal to 1, because our function, at least that we would like to define, if we define it from 1, then we can talk about the sum starting from k is equal to 1. And this is indeed what we have. So this is our function. And now the goal is to integrate it. It's an indefinite integral, or maybe, no, probably I should say an improper integral. We said that k is going to be equal to 1. I'm looking at x e to the minus x dx. So far, so good. There's actually something that we still have not checked. and that is whether the function is decreasing. So perhaps before I continue on with writing the integral, or perhaps let me actually go on and compute the integral, and then we will check for the decreasing property of this function later on. Because if the decreasing property fails, we cannot apply the theorem. But since I'm computing the integral and you're watching this video, then I probably have proceeded with this, and this gives you some sort of confirmation bias that the function will be decreasing. Otherwise, I wouldn't be doing this, right? Nevertheless, let us now compute this integral. I can write this integral as a limit as t tends to infinity from 1 to t of x e to the minus x dx. How do I integrate this? Well, it's just integration by parts. But if I take if I integrate this, I'll get I actually need to do this. So you choose e to the minus x to be your integrating factor, and you choose x to be u, then you get x, well, minus x e to the minus x once you integrate this, and minus the integral of this integrated version of e to the minus x. So the integration of e to the minus x is minus e to the minus x. This is what I meant basically. And then here you multiply by the derivative of x, which is 1. For a moment I thought I forgot how to do integration by parts, but I'm glad this is not the case. Now here we have two minuses. E to the minus x, if you want to integrate it, just e to the minus x. Very important note, you also have to include the boundaries. Very important. And here we also need to include the boundaries. Now here, well, e to the minus x, you just get the integral of this is e to the minus x. This is the anti-derivative of it. So I put the minus sign, I take this, I put it like that. Perhaps it is a good idea to combine these two together. And then, of course, you can take the derivative and verify yourself that this is going to be the answer for the exercise. And so we plug in our t's. Maybe I'll take e to the minus x as a common factor. Maybe take the negative term as well. You get x plus 1. I haven't substituted in for this just yet. And what are we trying to show here? Well, we're trying to show that this thing will converge in some way. Just to refresh, to keep in mind. By the way, all this time we're still in the bracket. If you're wondering, we haven't taken the limit just yet. This is what I mean. We get minus e to the minus t times t plus 1 minus e to the minus 1 and 1 plus 1. which is 2, I think. I hope that I can still remember what 1 plus 2, 1 plus 1 is. And so we are here, and I think we are ready to take the limit. So we're looking at the limit as t tends to infinity of minus e to the minus t times t plus 1. Maybe I'll write this as, I mean, this is a constant, so really it doesn't matter. I can literally write it, literally write this. So this part converges. The other part I still don't know. E to the minus t I'll write as a fraction. The minus sign is also not helpful, so I'll just remove it. Doesn't have anything to do with convergence. And now we have this limit. The question is, does it converge or diverge? The answer simply is that this goes to 0 because e to the t grows faster than any polynomial. So this is less than infinity, which means that the integral converges. And if the integral converges, then that's very good news for us, because the series must also converge. I must argue, of course, that this for this very specific series, what we will have is something that is decreasing. So the sequence that we're looking at, I still need to argue that it will be decreasing. This is really what's stopping me right now. So how do you show that a function is decreasing? Remember, this is a calculus class. Yeah, you take the derivative and you set it to be equal to 0. The derivative is going to be minus e to the minus x minus plus actually minus x e to the minus. This is the derivative of the function. Oh no, it's just here. It's just e to the minus x, and then when you fix x, you take this derivative. It becomes this. Yes, that's the derivative. I was hallucinating for a moment. Okay, so let this be equal to 0. We set f prime of x is equal to 0. Then well, I wrote then there. I don't need to write the implication symbol. Then clearly x has to be equal to 1, because there's absolutely no way on Earth or in any other universe that e to the minus 1 is equal to 0. Maybe if you define it in some ring or something like that, maybe it will work. But okay, so it's not absolutely impossible, but in our context, it's not possible. So this implies that x must be equal to 1. Now, what remains is to see whether this is a maximum or a minimum. So let's take a look at the behavior of the derivative before x is equal to 1 and after x is equal to 1. So we have this theorem which says that if it's positive, if the behavior is positive, then it's increasing. If the behavior is negative, then it's decreasing. Now, let's see what happens. We would like it to be this way, actually, because if we are starting from n is equal to 1, then we would like the function that we have here to be decreasing. And this will indeed turn out to be the case. So if you plug in a number that's less than 1, you'll get something that's positive. And if you plug in something that's greater than 1, you get something that's negative. And let's say you don't like this argument, or you don't want to argue for it anyway. So what you can do is you take a look at the function itself. This is a linear term, so x to the power of 1, multiplied by e to the minus x. And we know that e to the x grows faster than any polynomial. If you talk about e to the minus x, you're dividing by it. So in a sense, this function is rapidly decreasing. It decreases so quickly. I don't have a graph for this, but perhaps you could try to use one of the graphing calculators and see how its graph is going to look like. I'm pretty sure it's going to have something that's very steep. Well, it's going to be continuous, but it will decay very quickly, and that's what you can notice if you try to plot this function, for example. So if you argue that f is decreasing, and with that you also talk about this integral as being convergent, then the series must also converge. And that really concludes the argument. Nothing else to say.